So we've got the lecture part of the course covered. Today was supposed to be a buffer day, but we finished chapter 8 lecture last Thursday. So today we're going to do a discussion introduction of the lab and save the review for Thursday. And this is the last lab that we're going to have. And it's on, we're going to determine the molar mass of another compound. Let's see, how many ways have we done molar mass so far? We've titrated. Oh, we haven't done molecular properties, have we?
I think so.
No, melting point elevation. Okay, that comes next semester. So this one, we're going to determine the molar mass of a compound, particularly liquids, that are volatile. They have to be volatile. In other words, their boiling point should be, for our purposes, boiling point should be close to the boiling point of water. So we can get them into the gas phase. This work was pioneered by John Dumas, who I think, based on his name, is probably French, but I don't know. Since the Normans crossed the Channel and conquered the English, you get a lot of French names over there, over in England too. Let's see. I thought there was a little blurb on him. Maybe not. Here it is. Yeah. What Dumas proposed was that we use what we know about gases, because anytime you have a gas under ideal conditions, it doesn't matter what the gas is. So we can use that information to determine the molar mass of some unknown compound, because the gas laws are going to operate no matter what the gas is. So let's start by identifying what information do we need to know to determine the molar mass of any compound. I abbreviated molecular weight. That's just the way I was trained. Molar mass, molecular weight are the same thing. We need to know the mass, right? We need to know the mass of the compound, and then we need to know how many moles that mass represents. So it's mass per unit moles. Okay. So how are we going to get the mass of a gas? Believe it or not, you can. If your balances are accurate enough, if your volume is large enough, you can get an accurate measure of the mass of a gas. Okay. So the way we're going to do that is we're going to use a 125 milliliter Erlenmeyer flask. Right. Now that 125 milliliters is somewhere in here. That's not the whole volume of the flask. Okay, that's its designation. So what we need to know for further calculation is what's the total volume of that, and we're going to determine that in the lab. Okay, so we have this flask, and we're going to put some liquid in it, some unknown liquid. And then, well, actually, what we're going to do, we're going to have a small square of aluminum foil. We're going to have a larger square of aluminum foil. And we're going to have a copper wire and rubber bands. So we're going to put this one around the top and secure it with copper wire. Okay. But not until we put something in it first. Right? But we do need to know the mass beforehand. If we're going to know the mass of the gas, we got to know the mass of the container first. Otherwise, when we weigh the container later, there's no way to tell what's glass and what's gas. Okay, so you need to know the mass of these two right here. This would be what's called the, my mind just went blank. The tear. The tear mass. What that means is the container weight, the mass of the container. Okay, that's these two, plus the copper wire. Okay, those three gives you the tear mass. Then we're going to put some liquid in there and then put the cap on it and secure it. And then we're going to put this around the whole thing and secure that. Now, why do we need two pieces of aluminum?
Because of the condensation.
Mm-hmm. Right. If we use this one on the outside and secure it enough, then as you're trying to vaporize the liquid in a boiling water bath, you're going to get vapor all over the place. Okay, it's easy enough to dry off the outside of the glass, but if any vapor gets up underneath this little one or on it, then that's difficult to get rid of. Right, so what we do is we just cover the whole thing with this. Then when we pull that off, we've got, this is dry up here and we can wipe the rest. Okay, and we don't include this large one in the tear. So first thing you do is weigh the empty, dry flask with the small aluminum and the copper to get the container weight. Then we put the liquid in here and seal it all up and submerge it in a boiling water bath. Okay, so what that does is with these volatile liquids, it causes it to vaporize and it fills the whole space with vapor and drives out all the water. Oh, only if you punch a little pinhole through here and through here. All right, and we want to make that hole as small as possible. Any idea why? You want to make it small so that air doesn't have a chance to come back in. You want that whole space to be filled with vapor from your compound. Okay. Let's see. So we've submerged it in our water bath. And now that we've got it filled with vapor, we can remove the flask and let it cool. And when it cools, what's going to happen now? Well, the flask is going to be over here, right? And it's still got the small one on it. And we've taken the big one off. So it cools and we get a little bit of liquid in the bottom. Right? So if we're trying to find the mass, is there any difference between the flask, the mass of the flask before we cool it and after we cool it? No, no difference at all. This is condensed into a liquid, yeah. But it was the same contents as before. What we have to do is virtually ignore the mass of air. And that's okay because we've already got the mass over here, which had air in it, right? So all we have to do is ignore that little bit of volume that the liquid takes up as it refills with air. Now the tear is actually the flask, aluminum, copper, and air. So now we've got the air's back in here and we've got this liquid. Okay, once it comes to room temperature, you can weigh it again. And the difference between the two is going to be the mass of that gas. So we got the mass. Okay, now how do we determine the moles? We go back to the ideal gas equation. All right, so what's the pressure on that vapor that we vaporized? Now we're talking about this situation here. We've got vapor in there. What's its temperature? It's the temperature of the water bath. Okay, so that's why right before you take it out, you measure the temperature of the water. Okay, got that. Okay, that's a constant. How about the pressure? What's the pressure on that gas? Well, we don't know. I have to read it off my barometer in my phone. So that's barometric pressure. Okay, how about the volume? How do we determine the volume that the gas occupied? But when you put that small piece down here on the top, you want to try to keep it as level as possible so that when you determine the volume later, you know where to stop. Now we have two possibilities. We have the mass of the container here. So if we fill it up with water all the way to the top, where we think that the aluminum was stopping the gas, and weigh it again, then we can get the mass of the water. Okay, if you know the mass of the water and you go to I think it's in the back here. Yeah. And you know the temperature. Now the temperature of the water you put in there then is not that temperature. It's room temperature or the temperature of the water that you measure. Right? So it's a different temperature, like 21 or 20 degrees, something like that. And you look on this and find out what the temperature of the water is, and that tells you the density. So if you know the density of the water, and by subtraction, you know the mass of the water, right? The mass of the water, and you know the density of the water, mass per unit volume, then we solve for volume and we say mass of the water divided by its density at that temperature, and we got the volume. Okay? So then we just solve it for moles, and that goes right in here. Okay? Now that's the long way. You can also combine equations. And that's what they've done on the very first page. They've taken this formula and this formula and combined them. So if we want to solve for molecular weight, we want to solve this one for moles. And then we substitute this in there. Okay, so that means molecular weight is going to be equal to mass divided by moles. And then we just rearrange. Okay. So the denominator of the denominator is the numerator. So it's MRT over PV. And if you have those values, then you can calculate the molecular weight or the molar mass in one shot. Okay, that's all they've done there. Excuse me. Now, if we want to make it even simpler, we could take this formula and put it in there too. But we'd have two masses. We'd have the mass of the water and the mass of the gas. It might get a little confusing. So we'll determine the volume independently, and then we can put it into that formula. Any questions so far? Let's see. There's a sample calculation using this derived formula. Let's see. Now, did we have pre-lab questions in the handout, didn't we? Okay. I was trying to think because we didn't have any for the calorimetry lab. Okay. So let's look at some pre-lab questions and go to get our feet wet. All right. What happens to a real gas as it cools from, well, all right, before I read that question, what happens to an ideal gas as you cool it from zero to, from room temperature down to 0 K? What do we expect from an ideal gas? It stays a gas all the way down to 0 K, right? That's ideal. Now, how about real gases? And their example there is nitrogen. As it cools from room temperature to 0 K, first of all, would it disappear when it reached absolute zero? No. That's what we expect from an ideal gas. But a real gas, as we get colder and colder and colder, first it might condense into a liquid. And depending on the gas, if it gets even colder, it might turn into a solid. Right? So why is that? Why do gases condense into liquids and further into solids as they get colder? What has to happen in order for a liquid to form from a gas? Let's look at it another way. Gases have particles, and they're very far apart, right? So there's very, very few interactions relative to liquids and solids. And they're moving really fast, high energy, lots of kinetic energy. So when they smack into each other, they hit so hard and they just bounce off. So if there are any interactions, attractions or repulsions, they're overcome by the kinetic force, right? Those forces don't matter. But as we cool it down, we're slowing them down, we're reducing their kinetic energy. So when they do impact now, there's a possibility that they could interact. And as we get colder, they do interact. They start to stick together. Okay. So that's what happens when you get them colder, and that's based upon the kinetic molecular theory. Liquids allow those interactions to occur, but not so strong that they lock everybody into place. When they turn into a solid, all the molecules are locked into their positions. They can't move except to vibrate. Okay. And it's all due to the interactions. Now, some interactions are dipole in nature, like water. Right? Those are very strong interactions by comparison. Other gases like nitrogen, like water vapor versus nitrogen gas, which is a nonpolar compound, what forces do they have available? London dispersion forces, right? Didn't we talk about that? We didn't talk about London dispersion forces yet, did we? Oh, okay. Okay. Okay, maybe I'm introducing a topic that I'm jumping the gun. But the forces are a lot weaker. So you have to get the gas colder before it condenses. If the intermolecular forces are really weak, you've got to reduce their kinetic energy way, way down so that those forces can take hold and hold them into liquids and solids. Okay. That's one in narrative form. How about two? What does two say? What are the units of universal gas constant? Well, it depends on the calculation, right? If we have this one, and we're talking about gases only, usually this is atmospheres, that's liters, this is moles, and this is K. So R has to be in these units of measure. So if we want to find out how they're arranged, numerator, denominator, we just solve for R. Right? P, V over N, T. And then the units of measure would be, we usually put liters first. Liter atmospheres per mole. Okay. That tells you your units. Okay. Water freezes at, let's see, this is 3. Water freezes at 0 degrees Celsius, 32 degrees Fahrenheit, 232.2 K. Which is correct? Is one of them colder than the other? No. The phenomenon you're describing is independent of the units of measure. Right? It's going to freeze when it freezes. Right? Nature just does what it does. We're describing it in one form as 0 degrees Celsius, but we could just as easily call it 32 degrees Fahrenheit or 232 degrees Kelvin. They all describe the same phenomenon. So there's no difference, and one's not colder than the other. Kind of a trick question. How about 4? When can a real gas behave as an ideal gas? I think we talked about that one before, right? Real gases behave ideally when the temperature is high enough, like high temperature. And it goes back to that kinetic energy. They're moving with so much kinetic energy that interactions don't matter. Or high temperature, low pressure. And corollary to that is low moles. You don't want a lot of gas, a lot of moles of gas, which is correlated. These are related, right? So low pressure is sufficient. Low pressure just means that we're not trying to cram a whole lot of gas molecules in a small space. So the interactions are infrequent. Now, are the conditions met for our experiment? What's high temperature? As far as gases are concerned, high temperature is room temperature or boiling water temperature. Yeah. How about pressure? What's low pressure? Right here and now, right? Atmospheric pressure is low pressure for a gas. So yes, the conditions are met. And 5. A gas with a mass of 33.62 grams. Mass of the gas is 33.62 grams. I guess they went through that process, weighing the flask and then weighing it after. Occupies a 10-liter flask. Well, the volume is 10 liters at 27 degrees. Temperature equals 27 degrees C and 730 torr. Pressure, 730 torr. What's the molar mass of the gas? Okay. All right, in this case, 27 degrees is not that hot. So I'm assuming that what we're determining is the molar mass of a gas, and it wasn't a liquid before. Right? They just trapped that gas in 10 liters and were able to weigh it. Right? They didn't have to go through the process of making it volatile by heating it. Otherwise, 27 degrees it would have to have a very low boiling point. I mean, extremely low to be volatile at 27 degrees if it were a liquid. So we're stuck with these conditions. We've got the mass of the gas, we got volume, temperature, pressure, and the moles are unknown. So if we're going to use our equation, we want to go back to the this equation right here. Molar mass, I do it that way, is the mass of the gas times R times T over pressure times volume. So if R is going to be liter atmospheres per mole K, that one's got to be changed. This one has to be changed. This gives us atmospheres, this gives us K. So that would be 310. Calculated correctly. Nope. 300. Yep, 300, sorry. There we go. This one's correct. That one's correct. This one, 730 divided by 760. Let's see what that is. 0.9605. Atmospheres. Okay. Let's see. Well, you know, we don't need this one. That's been taken into account with the formula. And so we only need these values. So if we plug in the values, 33.62 grams, 0.08206 liter atmospheres per mole K, 300 K. Pressure is 0.9605 atmospheres. And volume is 10 liters. That should give us a molar mass. Now, if we were doing it in 2 steps, we'd have to calculate this first and then go into the ideal gas equation to get the moles. Let's see. Why does it do that to me? All right. 33.62, 0.08206 times 300 times, and then divide it by 0.9605 and 10. So I get 86 point, let's see. I better stick to 1, 2 grams per mole. I'll round it off to 2. Yeah, I'll round it to 2. Problem, well, you don't have the answer in there, do you?
On here?
Not in your, no. That's why I put it in red, so I'd be sure to know the difference. So, if we take that value and say, oh, wait a minute. Did I do that right? Oh, and identify the gas in 12.1. Okay. So, where is it? 12.1. I don't see it. Is it on another page? Oh, there it is. There it is right there. 86.2 is hexane. Okay. So if you're given a list, you know, kind of like a multiple choice, you could say, well, based on that list, that's hexane. Now, I wonder myself, if that's hexane, is it still a gas at 27 degrees? Hexane's volatile, yeah. But what's the boiling point of hexane? 69 degrees C? Okay, so that throws a wrench in the gears for this problem. Right? Because I don't think it's going to be a gas at 27 degrees. Right. And this temperature is the temperature of the gas when it's a gas, not when it's a liquid sitting on your bench. Right. So that's a flaw of this particular problem. What we're going to be using for this temperature is boiling water. All right. Okay. So we've got, I think that's the last pre-lab. I've got 6 volatile organic compounds, and you can just pick one, it has a number on it, and work with that one. Now, you may be able to take a guess at what it is if you smell it. Right? If you're familiar with some of them, like if you happen to pick acetone, everybody knows what acetone smells like. Nail polish remover. Or isopropanol, 2-propanol. If you happen to pick that one, sniff it, you'll recognize that one. Some of you may be able to recognize ethanol. Hexane, methanol, and pentane are a little more difficult to discern unless you work with them regularly. But we should be able to identify which compound you picked based upon your calculated molar mass. That's the objective. And once you've got a number, then I can tell you what it is, and you can put that into your notebook and compare your results with the expected value. All right. So let me see. Are there any, what about safety hazards? Glassware? Boiling water. Oh, yeah. And there's a hot plate there too. How about these compounds? I told you they're all organic compounds. They're flammable. Right? You don't want any open flames around them, especially in the gas phase. Right? Because I'm sure they've reached their, let's see, what's the proper term? Not flash point, but it's the concentration at which they will combust. There's a range. If you have too little flammable compound, it won't react. If you have too much, it won't react. There's a range in there where it will combust. I need to look that up. Let's see. Special notes. You have to have the correct atmospheric pressure, and I'll put that on the board. You've got to be sure your flask is dry at all times, unless it's in the water. Then once it's out of the water, make sure it's dry. Check for condensation underneath the aluminum. So when you put your small aluminum cap on there, be sure that copper is nice and tight, holding it, sealing it. And then you'll cover the whole thing with a big aluminum cap. Now I don't know, should I offer you this option? There's another way to determine the volume. It's not as accurate as getting the mass of the water and determining its volume by its density. And it's simply just filling the flask up to the lip where you think the gas was occupying, pour it into a graduated cylinder and measure the volume. Graduated cylinders are not that accurate. That's why I went to the density option. Let's see. Okay, there are your post-lab questions, and I think that's it, except for the appendix with the densities, water. That's it. Any questions?